Hi, AP Chemistry students. We are going to start Chapter 2 today. This chapter starts with a lot of the history of the atomic theory. So I just want to briefly go through how our idea of the atom has progressed. We can't see the different parts of the atom, and so our knowledge of the structure of an atom is purely based on experimentation. So the Greeks were the first ones that kind of classified things, but they chose 4 elements and kind of put everything into one of those. Democritus was a philosopher a long time ago who came up with the word atom. He had this idea that maybe everything was made of small pieces called the atom, and he thought that that was as small as you could get. So the word atom actually means indivisible because he thought you could not divide it anymore. And now we know, or we think, that you can divide the atom into much smaller pieces. There's a few laws that go along with this history. The first one is the law of conservation of mass that you've probably heard of before. It says you cannot create or destroy mass. And it basically just means we don't have the power to create something out of nothing, and we don't have the power to destroy something. So this is always the answer for why do we have to balance reactions, is because of this law. If you start with 1 atom of aluminum, you can't end with 2 atoms. You can't just create an atom of aluminum out of thin air. And so that's why we have to go back and forth across the arrow to make sure that it's balanced. The law of definite proportions you probably haven't heard of before. So make a note of this one. This just says that if you have a sample of water, that in that sample you will always have a 2-to-1 ratio of hydrogen to oxygen because our water is H2O. So it just means that if you have a certain compound, it will always have the same ratio of elements in that compound. That one is not too bad. It's this one that a lot of students struggle with. So make a note of this one. It's called the law of multiple proportions. And it says when 2 elements form a series of compounds, the ratios of the masses of elements will be in different ratios. To me, that's like blah, 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 blah. What did they just say? So let me just put it into different words. All this means is if you have 2 compounds that have the same elements. So for example, water is H2O, and hydrogen peroxide, like what you put on your cuts probably in your bathroom, that's H2O2, so it has 2 oxygens. So it's 2 different compounds, but the ratios of the elements are different. So water is a 2-to-1 ratio, and hydrogen peroxide is a 2-to-2 ratio. So I've seen this question sometimes on the AP exam for a multiple choice question, and they'll ask which of the following demonstrates the law of multiple proportions, and what you're looking for is 2 compounds that have the same type of elements but different ratios of subscripts. So like I said, H2O and H2O2. All right, that leads us to the atomic theory. We didn't do this one yet in honors chemistry. We're still getting up there, but Dalton is the first one that came up with what he called the atomic theory. Some of this we still believe to be true, but we have adjusted some of his laws and some of his ideas. Sometimes on the AP exam, they'll ask you to describe which parts of Dalton's law or theory. It's not law. Which part of his theory we still consider to be true, and which parts have we discredited, and why did we discredit them? So the first sentence says each element is made up of atoms. We believe that to be true. However, the indivisible part is not true. We now think that atoms can be broken down into smaller pieces. The second one says atoms of a given element are identical. Identical is a strong word. That means exactly alike, and they're not. Atoms of a given element have to have the same number of protons, but that's it. They can have various neutrons, various electrons, various energy levels. They just have to have the same protons to be the same element. So that is not something that we believe today. The next one says compounds are formed from the combination of atoms. We believe that. And the last one, atoms are rearranged during chemical reactions. We believe that to be true. It's more like the bonds are rearranged, but close enough. This is just one of the other ones they threw in with all these laws. Avogadro's hypothesis just says that if you have the same temperature and the same pressure and the same volume of a gas, then you have to have the same number of particles. And it's because of his hypothesis that you can use this conversion, 1 mole equals 22.4 liters. Again, it's got to be a gas and it has to be at STP, so we don't use that very much. Standard temperature is 0 degrees Celsius, which is the freezing point of water, and most of the time we're not doing chemistry at 32 degrees Fahrenheit. So we don't really use this very much in the real world. All right, the next one is J.J. Thomson. We didn't talk about this one in honors either. J.J. Thomson used a cathode ray tube, which is actually the science behind those old televisions, the big fat ones that have like a whole lot of stuff going on behind the screen, so not a flat screen TV. This is the science behind it. And what he was able to do was to put a stream of particles here and then hold a charge up, and he could see if the stream of particles moved toward the charge or away from it. And so he was able to discover that they were these little charged particles that we had never thought of before. And so he's credited with discovering the electron. He didn't actually discover the proton, but he thought that it must exist to balance out that negative charge of the electron. Chadwick, all you need to know about him is that he discovered the neutron. That's pretty much it. Millikan used something called the oil drop experiment, and what he did here is he sprayed these little tiny particles. He got them to go through a really tiny hole so that it was only like one little particle floating down, and then he was able to charge this plate. And based on how hard he charged it, like how high the charge was, he could get this little particle to float, to kind of suspend because of the repulsion of the charge. And so he could calculate what the charge on the electron must be. And so he used that calculation then to figure out the mass of the electron, which is really, really tiny. Marie Curie did some radioactivity, and we'll get into this when we do nuclear chemistry, but these are just some of the particles that she studied, which, speaking of which, if you have Amazon Prime, there's this new movie on Amazon Prime called Radioactivity, and it's about Marie Curie, and it is really good. So you should watch that if you get a chance. Gamma rays have high energy light, beta particles are high speed electrons, and then alpha particles are actually a helium nucleus that has a +2 charge. All right, this is the first one that we did in honors chemistry. So Rutherford did this gold foil experiment where he took a piece of gold foil and flattened it as thin as he could get it. He shot these particles at it, and his hypothesis was that they would all end up over here because it was such a thin piece of gold. But some of them ended up bouncing off, and so he used this circular detector, and he was able to see some of these particles bouncing back toward him. And so he was able to discover that they were hitting something that was really dense, and that's why he's famous for discovering the nucleus. Then we get to Bohr. Bohr is the first one that tried to organize the electrons. So up until Rutherford, he knew the electrons were outside the nucleus, but he didn't know how they were arranged. Bohr is the one that put them into these circles. So he said there are only certain regions of the atom where electrons tend to exist, and he called them energy levels. As you absorb energy, you can make the electrons jump out, and then as they come back down, because they're unstable when they're excited, as they come back down, they emit energy, and that is how fireworks work. So you may have done the flame lab in first year chemistry where you colored the flames, and we'll actually, we'll do something with that later on in this class. I'll at least give you a video to watch since you can't do it yourself. And then we get to Schrödinger, and he is famous for developing the current model of the atom. So he was the one that put them into clouds. And when I say clouds, I don't mean just like a fuzzy picture, because that's all we can see. They're clouds because of the word that's in capital letters up here, probability. So whenever you want to explain about the current model of the atom, you need to throw that word probability into your description. So what we can do is to plot like around this area right here, there might be a very high probability of finding an electron. But as you move away from the nucleus, the probability drops. So notice that it's shaded lighter. But then as you move away some more, it gets darker again because the probability goes back up. So as the probability changes, we can shade it, and that's why it's a fuzzy circle, not perfect circles. Also notice that the electron clouds are not always circles. These are a bunch of peanut-shaped clouds linked together. So this is just kind of a description. We started with indivisible particles, then we started to discover these positive and negative charges. Bohr is the first one that put the electrons into rings, and then Schrödinger is the one that talked about the probability of the electron, which is why we have shaded regions. So you should be able to look at these pictures and explain what's going on with these. The rest of this lesson I'm going to go pretty quickly through. We reviewed this in our review lesson, and most of you did really well with this. In honors chemistry, you had the full lesson for atomic theory. So nucleus is in the center of the atom. It has positive protons, neutral neutrons. They both weigh something. So it's small, but all of the mass of the atom is in that nucleus. Electrons are negative. They weigh almost nothing, so close to nothing that we just round it to nothing. And the valence electrons is a fancy way to say the electrons in the outer shell. they determine how reactive the elements are. So the protons determine the name of the element, but the valence electrons determine the reactivity. So determine the valence electrons. If you have a periodic table you can write on, you probably want to go ahead and label both valence electrons and oxidation numbers, which we'll get to later. Valence electrons, you want to start at the top, and you just count across to the right, but skip over the D block. The only exception is helium. Helium looks like it has 8 valence electrons because it's in the noble gas section, but it actually only has 2. Atomic number is the number of protons, identifies the element, and changing the protons will change the element. Mass is protons and neutrons. We don't include electrons because they don't really weigh anything. So to get the number of neutrons, you're going to take the mass and subtract out the atomic number. Isotopes, and if I'm going too fast, you can pause this. I only get to record for 15 minutes and then I get shut down, so I have to go quickly. Isotopes are atoms that have the same protons, which means the same element, but they have different neutrons and therefore different masses. So these two are an example of an isotope that they have. They're isotopes of each other, I should say. They're both carbon, which means they both have 6 protons, but notice that the mass of this is 14, which means it has 8 neutrons, and the mass of this one is 12, which means it only has 6 neutrons. So different neutrons, different masses, but the same element, we say those are isotopes. Average atomic mass is what is actually listed on the periodic table, and it's a long decimal because it's an average of all the isotopes. So every element doesn't have a certain mass because they can have different numbers of neutrons. Just like in the last slide, we saw that carbon could have carbon-14 or carbon-12. So which number do we put on the periodic table? Neither one. What we do is we take an average. And so they're able to figure out the percent of each isotope in a sample of carbon, and using those percentages, they can calculate the average. The next word is ions, so lots of vocab here. Hopefully you remember these from the review unit. Ions have a charge because they've gained or lost electrons. So the 2 words you want to think of for ions are charge and electrons. And there's actually specific words for each of those. Cation means positive and anion means negative. And remember, a cation, look for that lowercase t, it looks like a plus sign. This is just an isotope symbol, so you need to be able to look at this and understand what all these numbers are telling you. The mass number is this number up here, and remember that's protons plus neutrons. Atomic number is down here, it's just the protons. So if you wanted the neutrons, you would subtract these, so you could say you have 12 neutrons. And then this is the charge, which tells you what you have extra of. So this tells us that we have 1 extra proton compared to electrons. But we can't add a proton because that would change the element. So what you're going to do is take away an electron. So start with this 11. If it was neutral, it would have 11 electrons. And then you do the opposite of the charge. So the final answer there is 10 electrons. And again, we got that by starting with the protons and then do the opposite of the charge. And you can check that because notice if you have 11 protons here and only 10 electrons, you see how you have 1 extra proton, which means you have 1 extra plus, and that's where that +1 is coming from. And that's it for today.